I'm going to be using two notebooks, and they're on my GitHub page, github.com/pkofod. That's P in my middle name, and then you can find the repository JC 2017. Okay, so you can just clone it and follow along. One notebook, that's Optim.jl, should really be called like workshop. That is a Julia 0.6 notebook, and the figures is a 0.5 notebook because I just couldn't get Interact to work with 0.6. So yeah, but you can follow along, and yeah. So that's there. Let's see if this works. Cool. So welcome to the workshop on JuliaNLSolvers packages. So I'm going to be talking about mainly two packages in our organization. Optim.jl, which does optimization of univariate and multivariate functions. And NLsolve, which is a package for solving systems of nonlinear equations. So I'm going to be talking quite a lot, showing examples and showing some figures to sort of give you an idea about how these different methods work and where they fail and where they don't. But if you have any questions, just ask, raise your hand, and I'll try to answer them. Your questions, but it's going to go like this. I'm going to be talking and showing stuff, and then in the end there will probably be some time left, and you can work on some of the exercises that are at the very bottom of this main notebook, the one called Optim.jl. But you can also like try out different problems and ask questions. Yeah, so we'll figure that out. So there are going to be two topics today. The first one is on optimization. So I'm going to briefly present what I mean by optimization and what you should expect this package to be able to solve for you, and then go through the syntax and some examples, and then also present briefly a package that we have in the organization as well that's called LSQ Fit, and then just mention something, how you can do stuff outside of JuliaNLSolvers package ecosystem. And then the other part is on solving systems of nonlinear equations, and that is going to focus on the package called NLsolve. That's also in our organization. So Optim and LSQ Fit, they used to be in the Julia Opt organization, but earlier this year they had sort of a reorganization such that it was to only contain packages directly related to MathProc Base and Jump and Convex and all the backends. So we had to find a new home for Optim, and that ended up being JuliaNLSolvers. So it's maybe not the prettiest name in the world, but we just needed a place to stay. And in that organization, as I said, we also have LSQ Fit and a line searches package. And then we were joined by NLsolve that used to be in the EconForge organization, but NLsolve shares a lot of functionality with Optim.jl, so it made sense to collect them in the same organization. And they were kind enough to move it to our organization from EconForge and also allow us to use the MIT license. So that was nice. Okay, so the first topic is optimization. So optimization in a nutshell is when you're trying to solve a problem like this. You want to minimize some function f0 or if not, subject to some constraints such that all the fi's are less than or equal to 0 and all functions hj are equal to 0. So the first fi's, they're called inequality constraints, and the hj's are called equality constraints. So there are lots of different types of optimization problems, some with special structure, such as convex optimization, that has some very specific structure that allows you to prove some very powerful things about convergence, and you're sure that you're finding the optimal solution and stuff like that. But what we're going to be looking at today is what you might call just nonlinear optimization, even though other types of optimization can be nonlinear as well. So this is just unspecified nonlinear optimization. And it's going to be unconstrained, optimization, so problems where all the constraints functions are just identically 0 or absent, or however you want to look at it. Okay, so our job is to find an x that minimizes this function f that was f0 before. So yeah, we have to find this x that, compared to all other possible x primes, gives us a lower function value. Okay. So what could be some examples we could be trying to solve? Well, for univariate cases, we could be looking at a very simple quadratic. And here it's very easy to see that the global minimum is attained at the global minimizer x equal to 0. Okay, so this is a convex function, so this is can be certain that there is just one optimal solution, global solution. What about a trigonometric function? Well, trying to minimize this could cause problems for us if we don't think about what we're doing. So in the scope of Optim.jl, what we're going to be able to find are these local minima, all these values where the sign of x is equal to -1. And there are, of course, infinitely many of them, so you have to be a bit careful with choosing an initial x and interpreting your results. So this is just to say that when you're working with stuff that we might call nonlinear optimization, you have to be a bit careful about there being multiple minima, multiple global minima, and the next example here, we have a sine of x over x. We see that we have 2 global minima here and there, and then we have a lot of local minima. So the methods that you're going to see, if we initialize it here, it will have no chance of finding these 2 global minima. Just so you know what kinds of problems we're trying to solve. There are other Julia packages that will try to find the global minimum using global methods, but that's not the scope of Optim. So you just have to be a bit careful with interpreting your results. So these are local methods. Okay. So what about a multivariate case? Well, a test function or an example that's often used is the so-called Rosenbrock function. So here we have an x that is in Rn, and we want to find such an x that minimizes the function value f. And in the 2D case, we see that it's, okay, I see that Julia box didn't save my changes, but there should be a parentheses here, and then a square, and then this should be here. So anyway, in code, it is correct. So it's like this. So Optim.jl will try to minimize functions such as these. So, all right. Okay, I see. This is weird. This is sort of the wrong word version. Okay, anyway. So what is the scope of Optim? Well, we have some different types of methods for minimizing functions. We have derivative-free, and they're sort of like heuristic methods. They are like, they propose some rule that will probably give you a low value of your objective function, but it may not always be obvious why that is. Then we have first-order methods that uses the gradient to steer you in the direction of the minimum, and then second-order methods that uses the gradient and the Hessian to find minimizers and the minimum associated with those. Okay, so we have some special methods also for the univariate case, where you can provide some bounds on where you want to find your minimum within these 2 bounds, and then it will try to do that. But we'll see that later. All right. So as I said, derivative-free methods, they may sometimes seem a bit weird, but sometimes they do a good job, and sometimes they don't. So then we have, as I said, the first-order methods. They are usually much more efficient if you have a differentiable problem, but it may not be the case. But they will often be a lot faster and more accurate. And then we have the second-order methods. These are the Newton methods, and they're very powerful if you have the Hessian available, so this second-order derivative of a multivariate function. But they can also see severe limitations if you have very big problems and you don't have sparsity in your Hessian.
Hey, to calculate the first derivative and the second derivative, can you use only finite differencing, or you can also use dual numbers, or can you specify which you want to use?
So the question is that if you want to use a second order method, do you have to provide the gradient and the Hessian yourself, or can you just provide the objective?
Yeah.
And as we will see, you can just provide the objective, and if that objective is written in Julia, then you will be able to use automatic differentiation methods, unless you use stuff like blast calls and stuff like that in there that will give you problems. And then then you can use finite differences instead, but that might not be as accurate. And it might also be quite a lot slower. So you will be able to use that if you just have your objective and you don't want to spend time deriving the gradient of the Hessian, or you're not able to because you're not smart enough. I don't know. Not you, but yeah. Okay. So one heuristic could be the quite well-known method that's named after Nelder and Mead, and it's called Nelder-Mead method, and we have that in Optim. It sort of maintains an ND triangle, a simplex of points in the space where you're searching for your minimizer. And then it does some different you can interpret them as geometric operations on this simplex to try to always replace the worst point with a better point. And I'm not going to go into all the details, but I'm just going to mention that it will then follow these different rules and then try to find a better point to replace the worst point with. So you just give it an objective function, and it won't be using any gradients or Hessians or something like that. It will just use these simple rules to try to minimize your function. So then there's gradient descent, also a quite simple method. And this, I hope you're all somewhat familiar with these multivariate functions, but these almost circles, they're contour lines for some function, right? So at each, if you follow this line all the way around, then the function will have the same function value at all these x's. So this is a 2D problem, right? You have a two-dimensional vector you're putting in there. So then, as we move inwards towards the inner circle, then the function value decreases. So the gradient, if you don't know, is a vector that tells you in each direction, if you move x1 a little bit, increase x1 a little bit, and x2 a little bit, and x3 a little bit, how much does the function value increase? So as I said, the function values decreases this way, so the gradient is going to point that way. So the method of gradient descent is simply to go in the opposite direction of the gradient, right? So the gradient tells you partially in each direction how much the function increases. So if it increases, you should go in the opposite direction. If the gradient is negative, you should follow that direction. So that's the method of gradient descent. So to sort of stabilize the method and make sure that it will converge, we introduce this. So the search direction is just minus the gradient. Then to update from the current xk, our current guess of what the minimizer is, to the next xk plus 1, we take xk plus some alpha, which is a scalar, times our search direction. And that alpha is the step size. And that's found by something called a line search algorithm. And we will look at a few different line searches. Right? So that just makes sure that this scheme will sort of converge in theory. So that's an example of a first order method, a very simple one. It's based on the gradient, and you just go in the opposite direction of the gradient. So then, as I told you, the next step is the second order methods, and those are the Newton methods. So we have two different Newton methods, but this one is the one where you take sort of the same step as before. Your search direction is just the gradient, and then left multiplied by the inverse of the Hessian. So this means that you're incorporating sort of not just information about how much the function is increasing or decreasing, but also the curvature. So how much is the gradient changing when you change the x's? So that can be a very, very powerful method. But of course, I've written it as the inverse of the Hessian, but you could, of course, also have like h of xk times s is equal to minus the gradient, and then solve that system. We don't form the inverse, okay? But that's just to make it appear as in the same form of as in the gradient descent method. And then again, we have this alpha that S is the search direction, and then we allow the method to change alpha to see if we can, without updating the hashing, which is expensive, if we can like find a good candidate for our next xk plus 1. So that if you omit the line search, then there are a lot of problems where this won't converge. So it's quite important, and we will try to see what happens if we change the line search algorithms for some specific problems later. Okay. So this is just some interpretation trying to put the gradient descent and Newton method in the same framework. Is that if we so we saw a quadratic function before, and that was convex and had a global minimum. So the same is true for a multivariate quadratic function, as long as this P, which is a matrix, is positive definite. So if this is just some multivariate quadratic function, then to minimize this, we find the gradient of this function and set it equal to 0 to solve the first order conditions of the problem. Okay, and as I said, if P is positive definite, then the minimizer that we find will be the only one, and the global minimizer, and we will find the global minimum. Okay, so their x op can just be calculated as this, or again, using the P times x op equal to minus q, and then solve it using some solver. So why is that relevant? Well, you can see the gradient descent and Newton methods as methods where you create a quadratic approximation around the current iterate, which is called x0 here. And then what you do is you take this approximation of your function at x0, and you're trying to find a steps direction, s, that minimizes this quadratic function. And again, as long as P is positive definite, then we can find the minimizer of this approximation to our objective function. So it's not our objective function as such, but it's an approximation of it. And as you see, the search direction is minus P inverse times the gradient at the current iterate, and we then introduce the scalar line search parameter. So in the gradient case, P would just be the identity matrix here. And in the Newton's method, P would be the Hessian. Okay? So in that case, it's the second order Taylor approximation to our function around the current iterate. So that's just to put them in sort of the same framework, because I'm going to be showing you the two methods on some different problems. All right, so let's get to Optim. And so unless there are any questions about what kinds of problems we're dealing with here, I was just sort of trying to motivate it and make sure that we're all on the same page here. Okay, so we have some objective function. We can possibly calculate a gradient, and maybe we can calculate a Hessian. And then we have some different methods, and we're going to see how we specify, how we choose the different methods, and how they might do on different problems. Okay, so if there are any questions, just raise your hand, or yeah. Cool.
I was aware that you needed the line search parameter on the Newton maps, and
yeah.
So you actually do need that.
If you don't have it, you can have like cycles where you just go through the same axis in a cycle and never, yeah. And there are different types of line search algorithms, and they're in the NLsolve.jl package, the ones that we use, and I will show you some of the different ones and see that it makes us a difference as to how the xk plus 1 evolves. Right? Okay. So if you've downloaded the notebook and you don't have Optim already, you need to remove the comments. I was too scared to update anything prior to this presentation, so I commented out. But it shouldn't be that big of a deal. Anyway, you just using Optim as you're used to from Julia. Yeah.
There's 3 notebooks in this directory. Which
sure. As I said in the beginning, is the one called Optim.jl that we're using right now. So it could be called JuliaNLSolvers.jl, not .jl, but okay. And we're apparently at slide 11 if you want to follow along. Okay, so you set up the package like that. Okay. So what is the syntax of the main method in Optim? It's called optimize. And that's, when we say optimize here, we mean minimize. Okay? So if you want to maximize something, you can just minimize the negative of that. All right? So some packages have like a keyword where you can specify that you want to maximize. We don't, so you just have to provide, if you're doing maximum likelihood, then just put a minus in front of the objective, the gradient, and the Hessian, if you have that. Okay, so the way you use this package is you write optimize, and then the objective arguments, that could be the objective function, that could be the objective function and the gradient, or it could be the objective function and the gradient and the Hessian. And then you have to specify an initial x. As I said, these are local methods, so you have to tell us where you want to start. And then we will try to find a small value of x for you from that point on. And then you can specify method. If you don't, it will fall back to some default. And then you can specify options, and if you don't, then we'll just use the default ones. Okay. So let's just try to optimize some function, minimize some function. This is just the sum. If you pass in this case, 30-dimensional x, it will just square all the elements of x and sum them up. Okay, so a very simple quadratic function. And this is the OBJ function here that does that for us. And then we choose some random starting point, and then we just pass the objective function and the initial value. And as you see, it will default to the Nelder-Mead algorithm that I was talking about. So, of course, this is kind of a, you may think it's an embarrassing problem to show us the very first one. If we look at the output, you will see that the algorithm was Nelder-Mead. We started at some point 0.5 and 0.7. And the proposed minimizer is 0.05 and 0.025, and then some other things. But just by inspection, just by looking at the function, it's very obvious that the minimizer should be just a vector of zeros, right? And it also tells us that it tried to find a minimizer for 1,000 iterations. That's the default choice. And that it failed to converge. Because this criterion that we have for the Nelder-Mead, which is sort of like a variance of the points in the simplex around the centroid, so like the center of the simplex, that was not below some default value. Okay, it reached the maximum number of iterations, true, and we had 1,246 objective function calls. All right, so that was a bit embarrassing. It didn't work, but I just want to show that if you can provide the Nelder-Mead choice manually and the empty options constructor, and then it will do exactly the same thing. So objective function and initial value, that will show you that will give you the Nelder-Mead solver with the default options. So let's try a different method, right? It didn't work that well, so maybe one of the other methods will. And let's just try the gradient descent method that I told you about. That uses the gradient information, so maybe we'll do better on this problem. It sure is differentiable, and it's simple, so it should work. So if we specify the objective function and the gradient, and pass that, we can even to the optimize function along with an initial value and the choice of the gradient descent method, then it will give us this output. So I just want to note that when you construct your gradient function, the G exclamation mark up there, G-bang, then you have to give it two input arguments. G here is a vector that is used to store the gradient. And we do it like this because then we can update it in place during the optimization procedure. And then the second positional argument should be x, the current iterate. And I mean, if it's not obvious, then the gradient is just 2 times the current iterate. Because if you try to calculate the gradient, then you just element by element calculate the derivative, and then the 2 comes down, and you get a 2x1 in the first element of the gradient, 2x2, 2x3, and so on. And as we see, it actually found the the minimizer 0.0, even in floating point position, this is the 0. And the minimum is found to be the 0 as well. And it did so in one iteration. All right, so just to show you that line searches are important, this defaults to some line search algorithm, something that's called the Hagasang line search algorithm. It comes from our implementation of the conjugate gradient, which is another method for doing nonlinear optimization. And, but we can choose another one. Let's just choose a static one. And static here means that you just have a fixed parameter. So alpha is just some number. So we choose another line search algorithm by, in the method constructor, we specify line search equals, and then line searches, which is the package name. So the default would be Hagasang, like this. But let's just choose static instead. And that just defaults to an alpha of 1 all the time. So let's try that. That was premature input. OK. So we started at 0.74-ish and it's 0.3. And then we ended up at the exact same place. After 1,000 iterations, we didn't seem to improve our proposed minimizer at all. And you may be able to see this for yourselves, but what does gradient descent do in this case? Well, gradient descent was to take the current iterate minus the gradient. So, sorry? Do you want to? Yeah. So what happens is you just take x, and then the gradient was 2x. So you take x minus 2x, and then if the current iterate is x, then the next iterate is going to be minus x. So after an even number of iterations, it will just have multiplied by minus 1 1,000 times. Okay? So line searches are quite important when you want to use these methods. So let's just remove that because that was a pretty stupid idea. Okay? And you also see that the objective calls and gradient calls that match quite nicely with the number of iterations because we didn't actually do any line searching here.
Why in the I don't quite understand the definition of the objective function. It would seem to be
here?
Simpler if you said sum x dot caret.
Yes.
Is there
this is just the sum function that takes a function and then an array. Yeah.
Yeah.
Okay, so you. Yeah.
I think that function is exactly equivalent to sum x2 of x.
So we could do it like this as well. Yeah. But yeah, it's like the sum apps. Yeah. All right. So if we remember to use the line search here, then providing the gradient gave us quite a lot of a big advantage. So I had to tell it to use gradient descent here because that is not the default choice. If you just provide the objective and the gradient and an initial point, then it will actually default to something else, and that is LBFGS. Right? So I'm just using gradient descent here as an illustration, but it will default to another method. And LBFGS is a first-order method, so you only have to provide the gradient, but it will try to approximate the Hessian by looking at the difference in the gradients, right? So it will try to build an approximation of the Hessian as we go along. And LBFGS just means that it will not use the entire history of the gradients. It will just use some number of past gradients that you can specify. Okay. Let's just put it back in here. Okay. Yeah. So I showed you another multivariate function earlier, and that was the Rosenbrock function. So in Optim, we have a small set of problems that we use for testing the package when we update it. And there's not a lot in there, but there are some. And in there, you can find the Rosenbrock function, its gradient, and its Hessian. So you can sort of retrieve it like this. So I said probably equal to Optim.unconstrained problems.examples. And examples is a dictionary of problems where the keys are strings. So in this case, it's called Rosenbrock, so the key is Rosenbrock. And then we just called the objective rows F and the gradient rows G bang and rows H bang. All right. So let's try this wonderful gradient descent method that we saw before, right? It converged in one iteration, so maybe it will be great once more. So we started at some value minus, this is a 2D problem, the 2D version of the problem. We started at some value minus 3, comma, minus 4. And then we see that it does very poorly. Okay, so if you couldn't see it yourself, then the global minimizer is at 1.1, so it's getting there, but it's not quite there after 1,000 iterations. Yeah, so it's, as it tells you down here, it reached the maximum number of iterations, and that's why it stopped. Question? Yeah?
I'm sorry, I came in late. Can you just give me the address for the Jupyter notebook?
Oh, okay. Okay. So it's on GitHub, and I don't want to exit it because my name is PKOFOD. And then the repo is just called JC 2017.
Thank you. Okay. I'm sorry.
Oh, that's okay. So starting from minus 3, comma minus 4, we didn't do that well. So maybe we should just start at a different point, right? Minus 1, comma 1. And we see that it's getting closer, but it's still not quite there. It tells you that we didn't converge, and it stopped after the default 1,000 iterations. So what if we used Nelder-Mead? Will it do better or worse? Before it did horribly on a very, very simple function, right? The very simple quadratic function, it couldn't even find the minimizer. So let's just try to use Nelder-Mead once more. Starting from the same point, we see that we actually do converge in 95 iterations to something that's very close to 1, comma 1. So, of course, the point here is that these methods are in there for a reason, right? They fare, some of them are great for some problems and horrible for others. So for example, the Nelder-Mead does quite well here. And of course, I didn't have to specify Nelder-Mead here. So objective and initial point will just default to Nelder-Mead. What about using more information? So we had no information, only the objective, that did well. Using the gradient and gradient descent, that did poorly. So what about Newton's method? And so again, I specified Newton, it's just a habit, but we could just not do it. So here I provide the objective, the gradient, the Hessian, and some starting point. And it finds something very, very close to 1, comma 1 from the same minus 3, minus 4 starting point in 29 iterations. And we get the same convergence information as before. Okay, so it wasn't just because we used the gradient that we didn't converge. It seems to be that there's more to this story. Okay, so the choice of methods matter. So that's why it might default to some method, but you should try different ones to see if you get the same minimizer. Yeah. So let's try to look at why gradient descent did so poorly and Newton's method did much better. So as I said, I couldn't quite get interact to work on 0.6. So the other notebook is a 0.5 notebook. So I'm not sure what the resolution is here, so I could just. So this is the other notebook called figures.ipype. And we're going to be using interact optimum plots. So if you don't have those, then you should install them first. And that's just a pkg.add. Okay, so just because we're in a different notebook, I just pull in all the information once more, the objective, the gradient, and the Hessian. And then let's try to see if we can, I just want to make sure that this is active. Yeah, let's see if we can make some sense of what we just saw, that some methods worked and some did not. And then we just define these functions. All right. So now I'm going to be starting from the -1, 1 problem. It takes a little while for this to show, and that's because of the whole plus.jl situation where we cannot pre-compile all the backends. So there's quite a long time to first plot. But anyway, we're starting, this is sort of a contour plot, but where we filled in between all the contours. So the minimizer is over here at the red dot. And the yellow dot, that is the starting point, -1, 1. And this slider will allow us to go from the first iteration to the iteration 1000 where we saw that it stopped. Okay, so we're in this sort of valley here, and we just have to follow the banana all the way to the red dot over here. So let's see how it does. It does make some progress. Then it makes a lot of progress. We're at iteration 174 or in 59 now, so we got kind of far. So we'll see what happens. So we go all the way up to 300, 400, and then it grinds to a halt here. Okay, that was kind of disappointing, but it kind of shows the same thing that we saw in the output, that we got sort of close to 1, and it also, I mean, you might guess that if we just increase the number of iterations, we would get there, right? But it's doing so very slowly. So that was for gradient descent. Let's try from the other starting point that I showed you, -1, or I didn't show you this maybe, but -1, -1, and then this time you can't see the first axis, but that doesn't matter too much. This time we're going to start down here, and then we're going to see how gradient descent does and how Newton's method does. So again, the slider is the number of iterations. So we start at 1, and then we can increase it. All right, so Newton goes up and gradient goes to the right. And gradient finds its way into the banana, and Newton starts moving along the banana. And Newton's method is progressing very fast, and gradient is just grinding to a halt. Okay, so of course what you're seeing here is that Newton's method is able to use the information about the curvature here. So, for example, so the contour lines are like these bananas, like this. But that means that the gradient, for example, if you're here, then the gradient is pointing in that direction. So gradient descent is going to move in that direction. But so if Newton's method, because we're using the Hessian, so we're using information about the change in the gradient as we change the axis, that will know that this is sort of sloped like it is, like this banana function. So this is the reason why you want to use Newton's method if you can. Of course, we only have a 2-dimensional problem here, right? So if we have an x that is of a very large dimension, then gradient descent can maybe be better simply because each iterate is faster than Newton's, or maybe BFGS or LBFGS. Okay, so let's try to zoom in on gradient descent moving along this banana valley. So we're starting over here at some point, and we've initialized it at the same -4, -3. And then we just jump in at iteration 120, and we start at the blue dot, and the red line you'll be seeing is gradient descent moving along. And down here, you have alpha. So that's the step size that the line stretch is finding. Okay, one iteration, it moves to the right. But then, it's maybe hard to see on this, but if you can see it, then it's zigzagging. Right, and that's what I told you before, that the contours are these banana shapes. So actually the gradient here is pointing in that direction, so it's moving away from the minimizer, and then it's just zigzagging along, okay? And this has to do with what's called that it's ill-conditioned. So the problem is that these contour lines, they're like flat. So if the ratio of the height and the width of the contour line is, well, if it's in that order, then small, then gradient descent will do poorly. But Newton's method, because it's using the Hessian information, then it will not have the same problem. And as you can see, the alphas are very, 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 very small. You can't even see them here. It's so small, right? So that explains some of it. Okay, so what we can do is that we can just calculate the search direction for gradient descent in Newton's method, right? We calculate using the functions that we defined earlier, we calculate what is called store here is the gradient, and h store is the Hessian, So we can calculate the gradient step and the Newton's method step. And of course, there should be a minus in front. And you see that the gradient is very, very large because the Rosenbach function, it increases very rapidly as you move away from the banana. Yeah, so that's why the line search alphas are so small. So what I plotted down here is sort of, this is the line search problem. So the line searching is a one-dimensional problem, right? You have a current x, k, and you have a search direction, and then you move alpha around to see how can we minimize the function along this search direction. And for the Newton's method, the optimal alpha is somewhere around 1. So that just means that the Newton step is a very good idea to just take the full Newton step. Whereas for the gradient descent, very, very, very small alphas are optimal. Okay? So this is part of the story of this very, very slow convergence. All right. So this is just to show the effect of the starting. Can I go down here? Oh, I can't do it like that. Okay, I'll just go out to the notebook. So this is just to show you the effect of what's going on? Yeah. Let me just go down. The effect of different starting points. So we can move the initial x1 and x2 around using these sliders. So we increase x1. We see that sort of gradient descent is still not there if we start here, but if we get very close to the minimizer, then it will get there in, okay, very, very close. Okay, if we start at the minimizer, then it will converge, so that's great. Okay, but each white dot is 10 iterations, okay? So what if we change to Newton instead? Then we see that it converges very rapidly, right? It finds its way into the banana, and then it follows it all the way. And then I told you about LBFGS and BFGS, which is a first-order method that sort of approximates the Hessian using the historical information about the gradient. So sort of, but not exactly, but sort of like if you first difference your way to the Hessian using the gradients. And how does that fare? Well, it fares sort of the same as Newton's method, right? It actually, we initialize the Hessian as the, what's it called, the identity matrix. So the first step, as you will see, is actually just the gradient step. And then from there on, it will try to approximate the Hessian. And these are some of the different line searches that you can use. Hagasang that I told you about, Morituente, backtracking, or the cubic backtracking, and the quadratic backtracking. So you see the line search choice does have something to say on how quickly it will converge. All right, so I provided these interact figures, so you can try to change the problem as well to some of the other problems in Optim if you want to. All right. So as I told you, the reason that gradient descent is doing so poorly has to do with this condition number, or this conditioning that the contour shapes are very flat and long. So it's not just because of the banana shape. It's even in a simple quadratic function, we can see the same thing as well. This is the quadratic function with the identity p, right? So this is just the sum of x squared, as we saw earlier. And then here, gradient descent as well. But if we make the condition number worse, we will see that gradient descent starts to zigzag, as we saw in the Rosenbach function. So it's not the banana shape as such, it's more the poor conditioning. This is just showing the same. You can try this as well. This is just sort of the same now. And this is just to show the point I defined it up here. This is just to show that because we're initializing the Hessian as the identity matrix, then the first step of BFGS and gradient descent will be the same here. And we can try to worsen the condition number, and you will see that the black line is BFGS and the red line is gradient descent. So the first movement is the same, but then BFGS starts to approximate the Hessian, and then it converges in the next step, whereas gradient descent zigzags. So this hopefully explains some of the things we saw when trying out different methods back here in the old slideshow. So any questions for this? Mm-hmm.
So the examples that you had up there with the condition number all involved twice differentiable and a continuous function.
Sure.
Does the package also include things that use the subgradient for things
No.
like absolute value?
No, it does not. Okay, so the question is if we have some methods using the subgradient, so that's for non-differentiable problems, then there are some methods you can use there, but no, we don't do that. Okay, so are you thinking about specifically for stuff like convex optimization or just general nonlinear optimization?
For example, a common case of minimizing least squares is in regression problems, but sometimes you want absolute value.
Yeah.
That's not differentiable everywhere.
No, not at 0. Yeah. No, so we don't have any subgradient-based methods. No, we don't. Okay. Let me just go to where we started. Okay. So, and this is just another example where we have this function that is sort of like, it looks like this. So it's sort of like if you sat down at the beach, your butt cheeks would like make this imprint in the sand, where you have like these two, yeah. So in that case, we will have it looks like this. And then we have a gradient that looks like this. So what is the problem if we start at some x1 and x2 being 0? Then the second element of the gradient, x2 times x squared minus 1, is going to be 0, right? And then, no matter what line search algorithm we're going to use, then gradient descent, LBFGS, BFGS, Newton's method, they will all just converge to a point that is not a minimizer. So they will all converge to like just, I'm not going to name that, but the middle of the two butt cheeks. And that's not a minimizer, that's a saddle point, what's called a saddle point. So the gradient is 0 there, but it's not a minimizer. So that's also related to what I showed you before, that the initial x does matter. So when you're using these local methods, you may have to try to perturb your initial x a little bit and see if the minimizer that you found changes. Okay, so the lesson is don't blame Optim. This is sort of like not a feature, but the nature of the methods. So we sometimes get some issues on GitHub saying, why does it not converge to a minimizer, stuff like that? And a lot of time it has to do with this. These local methods, you have to try different initial starting points. So that's just in the nature of the methods. Right. So to the question, what if we don't have, it may be differentiable once or twice, but we don't have the gradient function or Hessian function in Julia. Can we just provide the objective? Yes, you can, as I told you earlier. We either use finite differences from calculus.jl, the package calculus.jl, or automatic differentiation using forward diff. So the default is finite differences, and there has been some discussion, should we use like some of these great packages, the auto differentiation packages instead? And the problem is that sometimes what you provide to Optim is not a Julia function. It may be something that calls out to something you wrote in Fortran or C. Or maybe use blast calls in your objective function, and then you're not able to automatically differentiate. So that's why we sort of thought that the safe choice was to fall back on finite differencing, but you can choose to use forward diff instead. So how do you do that? Well, this is just to show what the results look like if you provide the objective function, the gradient, and the Hessian, and start somewhere with Newton's method for the Rosenbrock function again. And it converges, as we see and saw. So what we can do here is to, if we want to use the forward diff package, then we have to do a little bit, put in a little bit more effort than just providing the objective. What you have to do is you have to create what's called a twice differentiable instance, and then you provide the objective rows f here, and then specify what type of automatic differentiation do you want to use? :forward is the forward diff, and if you say :finite, then it will use calculus.jl. You can, if you do it like this, then it will calculate the gradient and the Hessian using forward diff. But you can also, you might have the gradient in like handwritten code, and then you can also provide that, and it will just calculate the gradient. And the reason why you need to specify a point here is that it needs some seed for the forward diff, all the forward diff config cache variables to be created. Okay. But if you provided your initial x here, you don't have to provide it when you then call optimize on this twice differentiable. Then you just put in the TD variable and the method that you want to use. Okay, so if we run that, we see that it is the exact same solution as when we used the functions that we had written ourselves when we used automatic differentiation. And we can also, as I said, if we just pass the objective and then some initial value, then it will also give the exact same answer, but this time using finite differencing, because that is the fallback method. Okay? So you can do that. And I mean, a lot of times it will work well, but the problem is if x is of very high dimension, then these finite differencing calculations may take a long time, and it can severely hurt your performance. Okay? So how do you choose different options in Optim.jl? Well, there are two types of options. There are the options that are related to the methods as such, and you put those options inside the method constructor, as we saw. Right? So this is stuff like the line search method and other like tuning parameters that you might be able to give to some method. And the other ones are more generally for optimize, and those are the gradient tolerances, or the maximum iterations, and stuff like that. So yeah, just an example. As you saw, you can tell what line search to use by using the line search keyword in your method constructor. And there are some different ones. There are the Morithorente, which is often pretty good, but not as robust as the Hakasang one, which we took from the conjugate gradient implementation by Hakasang. Then there's backtracking, which is used a lot also in like theoretical work to show that you will get convergence in some problems. Strong Wolf, you can look it up in the linesearches.jl package, what it does. And then the static, which is sort of like a learning parameter in machine learning. You often just specify one step size, and that is what static does, as you saw earlier. Right? So if you want to provide more general options, this is the same. You provide, for example, all the objective arguments and the starting value. You could provide a method here, and then the options. So in this case, we're setting just the number of iterations to the default, 1,000, but it could be 10,000 or like 100,000. It doesn't matter because it converges after 4,600 iterations. Okay, so this is the one that we saw that didn't converge earlier using the default, but increasing the number of iterations to a lot, we see that it actually did converge after 4,600 iterations. But that's still a lot for the very simple quadratic function. So there are, as I told you, there are other options that you could provide. For example, G_tol is the gradient tolerance. You can also tell it to stop after some time limit, so like a clock hour time if you don't want it to run for too long. But that's all in the documentation. Okay. So what if you try to optimize some function and it didn't converge, and you want to sort of look at how did the x's and the function value evolve over time? So maybe that can give you a clue as to why your problem isn't working out as you hoped it would. So then you can, in the optim.options, the general options provide set these keywords store trace to true, show trace true, and then extended trace. You can set that to true if you set store or show trace to true as well. So extended trace will store a lot more information that you might not want to store, because it can, if there are a lot of iterations and the problem is very big, then it can consume a lot of memory. Yeah, So that's just, as I said, now we're taking another example called the Hosaki function. And we're passing the function, the initial x provided by the dictionary here. And then we set the options, show trace to true, and we will see how NLDermeed evolves as we move along. So this is the best function value at some iteration, and then the convergence measure, which was like the variance around the center right here. And for different methods, for example, here we have LBFGS, it will show some other information, right? Because there, that variance measure doesn't really make sense. So here it shows the norm of the gradient instead. And we see that it decreases a bit slow in the beginning, and then it has a very rapid convergence because the Hessian approximation becomes very good. Okay. So this is with the extended trace. So this is a bit more messy, but this is for NLDermeed again, and you see it stores the best function value, the convergence measure here, and then what kind of step did we take? I told you there were different rules. It tried different types of steps, and it will record what type of step it took. So, for example, there's a step type called shrink, where it just moves all the points closer together, and that's a very bad sign if you see a lot of shrink steps. That means that it's not able to replace the worst point by a better point. So it would just try to shrink until all the points are close together, and it will say it converged. Yeah, and the same for, if it's a line search based method, it will also, if you set extended trace to true, then we'll also record the step size and the gradient at that point. So you can see that if your x is of a very large dimension, then it will store a lot of these arrays of very large dimension, and if it runs for 10,000 iterations, it will consume a lot of memory. So that's why it doesn't do it by default. This is just for the Hessian. You see it also stores the Hessian at the different iterates. Yeah. So if you have, if you store the trace, then you can grab the trace using the trace function, Optim.trace, and we don't export it just not to like pollute your namespaces. Yeah. Okay. So the Optim.trace is part of the general results grabbing API. So once you have stored your results from the optimization attempt, then you can use different functions to grab the different results. So for example, Optim.minimizer of your results will return the array that is the potential minimizer. But you can also access it by writing res.minimizer, but I would ask that you do not do that. A lot of packages does this, and this means that when we change something in the package, it's impossible to deprecate it. So that's why we have this function API instead. So minimizer used to be called minimum a year ago or something like that, and that's the wrong term for what we actually mean. So when we had to change that, then we had to sort of make pull requests to all the packages using the field directly. So that's why we have this function grabbing API, even though you can actually just access the field. Okay, so there are lots of different functions. So the minimizer, minimum, how many iterations, what was the trace if you stored it, how many gradient calls were made, etc. And these are all found in the documentation as well. Okay, so as I told you in the beginning, we have a special sort of methods for univariate minimization if you can provide some bounds where you want to find the minimum. And but you can also just use like the regular methods that I just showed you for univariate minimization. And I'm telling you this because we've also had a lot of issue on GitHub asking why can't you use gradient descent for univariate methods? Well, you can. You just have to provide the initial x as an array. So something is wrong here. This is what is done here. So here I just provide, like, you provide a function. It's a univariate function, but you have to specify it as like an array if you want to use the multivariate. So this is a multivariate problem, but just a one-dimensional multivariate problem. So then you just have to be careful with this. And then the initial x has to be an array and stuff like that. And then you could use, for example, accelerated gradient descent, which is one of our multivariate methods. Yeah. And as I said, you can also use the bound the bounded version. So there you have, the bounded versions of the univariate optimization, they don't use gradient information. So you should only pass the objective function, the lower bound and the upper bound, and these are just scalars here, and then one of the two methods, which is either the golden section or the Brent. Yeah. So, yeah, this is just what I just said. Defaults to Brent's method. Okay, any questions so far? Okay. So one of the things that just got merged was that we want to try to take advantage of the Julia type system more than we are currently. So one thing that you can do is to allow dual numbers to take part of these calculations. So why would you want to do that? Well, say you need to solve some equation g of y, and you want to set that equal to 0. Then part of evaluating your g involves minimizing some quantity f over x for a given y that you enter into g. So if you want to use a gradient or derivative-based method for for solving this equation, then you need to be able to find the derivative of this problem with respect to y. So say we have some function f of x and comma y that looks like this. Then we can find for a given y, we can find the minimizer x star, which has some value given some y. And then we can find how much the optimal value and how much the minimizer changes as we change y. Okay, so remember, we're changing y out in g to make that 0. And that then has an effect on the result of this minimization problem. So then we can do it by hand like this and find that, okay, at 1.1, then the derivative of the result of this problem is minus 1,331. But we can also use forward diff, the automatic differentiation package, to do this for us. So we just specify our function like this. There's something wrong with this. I think JuliaBox didn't save my... OK. And no, this was correct, sorry. It was correct. It's just the indexing doesn't matter here. But OK, so we specify the function, and then we make a new function that is our capital G from before. And that function does what? It calls the minimum function from Optim. That's the one that tells you what the minimum was, given the optimization results of the optimize call to this function that is a function of both x and y. And then we have some bounds. And then we use forward diff to evaluate the gradient of that at the point 1,1, and we get the same result as before. So it's a bit trivial example here because we could just do it by hand. But what we haven't done yet, but it should be possible as well to do this for multivariate function problems, and then it will be, I think some people will be able to use this for these sort of nested problems. Okay, so this is just to say that Optim works well for a lot of problems, but as I told you, these are only local methods. So if you're using Julia and you don't need to use stuff like automatic differentiation and stuff like that, then there is an interface to the very well written and very well tested and widely used package NLopt, and that does constraint optimization, global optimization, and a lot of stuff that we don't do yet. Great. Okay. So, okay, the following section is just sort of an example of a nonlinear, a special kind of optimization problem, nonlinear least squares. So this is the LSQ fit package that is in our organization as well. So here our problem is, it does fit into our nonlinear optimization framework that we looked at before, but there is some special structure. So the objective function is a sum of squared residuals, where the residuals are some yi's that are some observed quantities, and then a model of what those quantities should be. Right? So this is, maybe you are observing some signal with some noise, and you have a model for it, and you want to find the parameters that characterize the model that generated this signal that you measured. Okay, so as I said, your problem is that you have some observed y's and you think that they come from some model plus some noise. And that's where LSQ fit comes into the picture. So say we have some model here where for a given x, the value of whatever quantity we're trying to model here is going to be this. So we can plot it for some, this is just the model and then generating some data. And then we can plot the model function is the blue one, and then some realized measurements that are the dots. So then LSQ fit can try to fit this curve to the points. And you have to provide your model, an initial guess for the parameters, and then you can provide sort of Jacobian information and lower and upper bounds on the parameters and weights. If you want to weigh some measurements, you want to put a low or high weight on those, then you can do that as well. Anyway, as I said, the syntax is quite simple. You just provide the model, the data, x and y, and then a starting value. And then we see that we plot the true model and then the estimated model. So this was quite kind of a simple problem, right? So we're doing quite well, but it was a quite simple problem. So in the beginning, I showed you sort of like a weird wavy function that was sine of x over x. So it went like this, and then sort of phased off. So maybe we observe some signal that's generated by this function, where it should be a t in here. And we have some measurements, but maybe our equipment is not that good, so we can't just trust our measurements exactly. So we want to use LSQ fit to estimate a model of these signals. So the model is like this, and we generate some data. We use curve fit to fit the curve to the data, and then we plot the result here. So for this realization, we don't do that well, right? The blue one is the estimated one, and the green dots are the data, and the true curve is like that. So that's just to say that the very, very nice result we got before, that depends on your data and how complicated your model is. So we can try to, maybe we have 100 samples instead, maybe we do better. And it seems like we do, right? So just bear that in mind when you're trying to fit this curve that, yeah, sometimes you need more data if the function is very weird. Okay. So any questions so far? None. Okay. So the last part that I'm going to be talking about is NLsolve. As I told you, it comes from the EconForge organization or EconForge project, and it was transferred earlier this year to JuliaNLSolvers. So it uses a lot of the same underlying structure and types and stuff like that as Optim does. But we're still working on trying to unify the syntax and the interface and stuff like that. So what does it mean to solve a system of nonlinear equations? Well, imagine that you have these functions f1 through fn, and you want to solve this system of all those functions. So again, this is just like with optimization, right? Sometimes you have a lot of structure. That means that you can use some very powerful methods. But if you're using NLsolve.jl, you probably have some function where the fi's are just nonlinear, and you don't know a lot about the structure, but you still want to try to find some solutions to this system of equations, right? So we have n functions, and x is also n-dimensional. Okay? So n functions and n x's. And we usually write just f of x is equal to 0 for sure. Okay, so one example of this could be fixed point problems. You have some function x, and you want to find an x such that when you put your x into it, it just returns the same x. So is that a problem like the one we had before? Well, if we define a new function f tilde of x that is just f of x minus x, then we have a problem like the one before. So this, sometimes you want to do this, sometimes you don't. So some of these fixed point problems, they have some very specific structure that you can use, but if they don't, then maybe you can try to use NLsolve. So I've used NLsolve personally to do this, where the fixed point problem is some system of best responses in some game between different agents. In a case where I know that there's only one solution, so I can just try to see if I can find a solution, and if I do, then that is my solution. But of course, if you've done any game theory, sometimes these f's can be correspondences, and then it won't work for you. So, but that's, again, sometimes you can use structure, sometimes you can't. So the methods that we have in NLsolve, they're just like the second order methods, you could say, from before. So there are two different types of Newton methods for solving these equations. But we don't have any objective function this time. So when we're trying to, this up here is just like trying to solve the first order conditions, right? Trying to set a gradient equal to 0. But when we were optimizing, we had some objective function that was telling us if we were going in the right direction or not. And we had some measure of what we thought was good and bad. But here, we're just looking for some x's that will solve this system of equations. All right? So, but still the methods are just like the second order methods that we had. And then instead of when we had an objective function before, we will have something called a merit function, that is a function that's telling us how much we deviate from these conditions. Like how far are they from 0, the different fi's. Okay, so f here, if we want to like try to compare it to what we did in optimization, f is just like the gradient. It's a vector, an n-dimensional vector, and then the Jacobian of that system is n times n. So this is sort of like the Newton step that we saw, but it's not optimization, so it's not really the same, but it's clear that the methods are related, right? Yeah, there should be a minus there. Okay, so what is the syntax of NLsolve? Well, you provide this function that calculates the vector of f i's, and then you can provide a Jacobian if you want to. If you don't, then it will use finite differencing. And then you have to provide an initial x, and then there are some keyword arguments that will sort of, you can use them to set tolerances and stuff like that, maximum number of iterations. So this is one of the parts where it deviates from the Optim interface, the keyword argument style of setting options. Okay, so as I said, it's not the same as optimization, but we can still try to solve the first order conditions from the Rosenbrock function problem using this NLsolve, right? So this is just to have some system of nonlinear equations that we want to solve. Then we could just use the gradient, set the gradient of the Rosenbrock function equal to 0. And if we do that, then we just have to grab the problem from Optim still, and then we write NLsolve, and then we, this is very unfortunate, then we have to flip the order of arguments, because in NLsolve you provide here y is your current iterate, and here y is the current iterate, and x is the array that stores the current gradient, not the gradient, but the f vector. So this will change in the future. This is one of the places where we still differ due to the fact that Optim changed this recently with the latest tag. So it's sort of more Julian to provide the first positional argument. That should be the thing that is changing, and then the rest of the arguments are the things you use to update it. So that's why we want to change it. But as we can see, we found a 0 of this system of equations, and that just happens to be the 1, 1 that we also saw was in the optimization case was the minimizer. Okay, so the butt cheek function, we can try to solve this system of equations again that we saw. So the first equation is quite easy to solve, right? X equal to 0, you just choose x equal to 0. And the second one is also quite easy to solve, but let's just try to plot it instead. So here we see that having set x equal to 0, there are 3 different solutions to this problem that we want to solve, right? We want to solve the system of equations. but we're not minimizing anything. So here, the 3 different solutions are equally good in some sense, right? Then it's up to you if you, depending on the problem, then you have to sort of, yeah, I don't know what you want to use, what you're analyzing, but the different solutions can mean different things. But it is different from optimization because we don't have any like way of ordering these or saying that one should be the solution or the other. So the 2 points that in the optimization case was minimizers, they are solutions here, but the saddle point is also a valid solution. Just to say that there is, even though it seems like we're solving sort of the same problem, it is different things we're trying to achieve. Okay, so this is just trying to show you what it would look like if you were writing it manually instead of just grabbing it from Optim. As I said, the butt cheek, the B is for butt cheek, and then function bang. X is the current iterate, and the vector that stores the F vector is the second positional argument. Yeah. But other than that, this is much like Optim. And then you can also provide a gradient here, or this is the Jacobian, but NLsolve has always called the G anyway, but this is like the Jacobian. And you can also provide a function that calculates the F vector and the Jacobian at the same time. And yeah, but anyway, you can solve these systems of equations. So as I told you, there are 2 different methods. The truss region method is a Newton method, and the one's called Newton is a Newton method with line search. And as I told you, if we're going to use a line search method, that means that we have some objective function somehow to put a value on how good different steps are. And we use something called a merit function, which is just some function that measures how far we are from satisfying the conditions that we set up. And as you can see, this is another point where NLsolve deviates from Optim because we have to set the method by a keyword argument here, method equal to truss region or Newton. Yeah, so it's not as finished, and there are some different PRs. Some need to be updated, and they're mostly derivative-free methods. There's a method called Broyden's method, which is widely used, but we don't have that unfortunately yet. And then there's also another one, which is a newer one that is coming. And then we need to unify the interfaces. Okay. So at the beginning of this at the end of this notebook, there are some exercises that you can do if you want. We still have time, and then I can help you if you need any help. But you can also try to, if you use unconstrained optimization, but you're just new to Optim, then you can try to work on that, and I can also see if I can help you with that. So before we end, I just want to show you something else. In the repository, you will find also a folder called Coordinator and a folder called nReset. So nReset this is a optimal control problem provided by Asbjørn Reset, who's contributing quite a lot to the line searches package. And he has made this example where he uses the bound univariate optimization functionality to do part of this optimal control. And you can use that as an exercise as well. And then there are some pictures from Christoph Ordner, who's a professor at University of Warwick, professor of mathematics. And he's also contributed to the line searches.jl package. And this is just to show you something to answer the question that we often get, is Optim fast? Is it as fast as MATLAB? Is it as fast as something else? And it's kind of I understand why people ask that, but it's sort of an ill-posed question for a lot of reasons. But many times, the most expensive thing that will be part of your optimized call is going to be evaluating your objective, your gradient, and your Hessian. So I think that the answer is that yes, Optim is as fast as MATLAB in many cases, because I mean, when we're solving for the search direction, we're using backslash or maybe some other method, but it's mostly the same as in MATLAB, just calling out to the same linear algebra libraries. So the question is really it's not how fast the code runs, but if the choices we have made for line searches and different parameters, if they're good or bad. So Christoph, he's working with a lot of different things, but for example, he's working on clusters of silicon atoms. So this is a collection of silicon atoms. They're in a crystalline structure, but there is a problem. And that problem is that there are some defects inside of this crystalline structure. So for example, here, there's an atom too much, right? They should be equally spaced, but there's just one in the middle. Or there could be missing one somewhere. And then when you're working with these sorts of problems to design different, materials, then whatever the analysis of these things, it ends up being a minimization problem. So Kortner, being a contributor to JuliaNLSolvers, of course wanted to find out how using Optim compared to using ASE, which is like the standard software for working with these types of models. So in ASE or ACE, they use an LBFGS implementation for doing the minimization problem of working with these structures. So down here, I mean, you don't have to be an expert in this field to understand what is going on, but down here we have number of force evaluations, and you do these when you evaluate the objective and stuff like that, yeah.
Do you know what the dimensionality of that optimization problem is?
Yes, so the question is, what is the dimensionality? So in the picture I showed you, there were 4,000 silicon atoms, but that increased, that's a very small problem. Okay, so but I asked, as far as I understood, these numbers are for the 4,000 case. So but it does scale, but these are just because he didn't have time to run anything larger. But the main point here is that the important thing about solving this problem fast is minimizing the number of force evaluations. And minimizing the number of force evaluations has nothing to do with how fast you're solving for the search direction and stuff like that. And this takes a lot of time, and a lot of energy is spent on doing this. I mean, like not effort of people, but energy from a power plant of doing these analyses worldwide. So I mean, a lot of power. So being able to reduce the number of force evaluations can really affect power consumption, but also what types of analyses you can do. So what he did was he tried to use this ASE, which is like the standard software that a lot of people use, and then he tried to formulate the problem using Optim instead. So the blue one is using the Hagasang line search that you saw earlier. And that is really not something that LBFGS is born with. It's not part of the original like convergence theory. So Kortner tried to use some other line searches that we have as well. And for example, he tried the Morifuente, and that, I mean, you can see the decrease is like very large. And then you have the conjugate gradient, which is another method that you didn't see, but you can try to work with that yourself. And then the last one is the professor of mathematics fine-tuning line search and using a preconditioner that we haven't talked about and stuff like that, and then it was very nice. So I think when people ask if Optim is fast, the interesting answer is not really if all the elements of the different methods is fast. For Christoph, and I'm speaking on behalf of him, but this is what he told me, the important thing for him, when he did this, he was kind of new to Julia. But it was very easy for him to look at the code, make changes, swap in his own line search and stuff like that. And that is something he could not do in this ACE software. So is Optim fast? Well, in some sense, yeah, it is, even with the defaults, but it's also very flexible. So it allows you to very easily read the code, try different things, and make choices that are important for your specific problem. So another project that is using Optim.jl is Celeste.jl that has a keynote speak tomorrow, I think, or maybe the day after. And I mean, they're doing very large-scale analysis of information from telescopes, trying to find and characterize stars. So I mean, is Optim fast? Well, it's fast enough to process like huge amount of data, doing very advanced analyses. I should say that it's not that weird that they are using Optim, because the people behind Celeste, they provided the Newton trust region method for Optim, so it was just in their project before. But yeah, some projects are actually using Optim to a great advantage. So, any questions?
I guess that triggers, that's related to my previous question. I was thinking a little bit surprised at how high you could go with the dimensionality in this. I would expect that you'd be using matrix-free methods to do that. Are you using real subspace methods? Do you have that capability to do the linear algebra in
So the question is, do we have methods that can handle these Hessian, well, matrix vector operations, but really Hessian vector operations, and without forming the Hessian and doing the complete, like, store it in memory for very large problems? So the answer is that no, we don't have it, but there is an open PR for it. We're just trying to find out what the best interface is. But the functionality is there in a pull request. Let's see if we can find. Oh, this is not it. Oh, this is solve. Oh, we can just go back. So there is a pull request for that. Krylov trust region method, conjugate gradient. Yeah. So this is Jeff, who's on the Celeste project. Yeah. He has an implementation of a Krylov trust region method, and it works, but it didn't. Apparently, it didn't give them the improvements that they had hoped it would, but it's coming soon. We just need to find out the best way to have the users provide this function for calling the Hessian vector operations. Okay, so that's a great question. And another great question would be why we don't have constraint optimization in the package. And the answer is that we do have box constraint optimization. I didn't want to show it because it's very simple. You just provide two vectors of bounds on your axis. But Tim Holy, who's a very active Julia contributor, he has the constraint optimization episode 2 pull request. It's episode 2 because he also had an episode 1 that was made, like, I don't know, several years ago, and it never got merged, and then Optim moved on and everything changed, and then it was really, like, I've tried to what's it called, like, resolve the conflicts when trying to get it rebased a few times and just gave up, and Tim has done the same at least a few times. So in the end he decided just to write a new this is a primal dual interior point method for solving constraint optimization. So he made that. And again, time, so people are happy about this. But then time moved on, and now master has moved again, and it's sort of, so if someone wants to spend JuliaCon rebasing this, that would be great. So actually, this implementation is quite good. Like, the obvious choice would be to use IPOpt if you were to do something like this, and you wanted a free solver. And Tim has done some benchmarking on the problem, and for a lot of problems, I don't want to explain all these graphs, but for a lot of functions, they're actually doing equally well. And on some problems, IPOpt is doing better, and on some problems, this is doing better. But when this gets merged, I think the usefulness of Optim is going to increase a lot. Because currently, we do need a constrained optimizer to be like a viable choice for a lot of things, because it's important to a lot of people to be able to solve these problems. But this needs to be sorted out, and so this is sort of a free time project for me. So I just haven't had the time to fix these conflicts yet. But other people are very welcome to contribute. So any other questions?
Can you handle cases where the Hessian is very sparse, like the cells, they specialize the sparse libraries?
Yeah, so that's another no, but also pretty much just a question of us finding out what we believe is a good interface for that, because you saw the twice differentiable type, and we use that, 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 the one that we used when we were using automatic differentiation. The way that that is written right now does stuff that sparse matrices are not very good at. So you shouldn't index into and update sparse matrices, and you shouldn't do in-place operations on sparse matrices. And a lot of the code is written like that. So we need to refactor a bit of it, so we can use multiple dispatch to such that subproblems get handled correctly if it's sparse. So that is kind of a big deal if you want to use Newton's method for large-scale problems, right? If you have some sparsity patterns that you can take advantage of. We don't do it yet, but I mean, technically it's not going to be a big change. It's just a syntax and a code refactoring problem. So again, PRs are very welcome in this regard, but yeah, maybe we should prioritize that because it is an important thing. Yeah. Because as n just gets moderately big, then Newton's method is not going to be like viable.
You said you can handle problems with real variables.
Yes, if there is sufficient sparsity in your Hessian, yes. And other things we could do is we could also have special, you saw the twice differentiable type. We use those internally. That just holds all the different functions and some of the cache variables and stuff like that. But we could also have different types for separable problems. Then you can do some efficient things. And yeah, we could look into that in the future. Yeah. So, actually NLsolve for solving systems of nonlinear equations, that has some support for sparse Jacobians. I'm not sure it's done. I mean, that uses the whole in-place stuff, so that's why I didn't show it today. I don't think it's a very efficient way of doing it right now. But we should redesign that, and we should do it at the same time as allowing for sparse Hessians. Yeah. So that's another way of enabling like high-dimensional problems that is different from the Krylov method. If you have sparsity, you can just like calculate the sparse Hessian and just do your normal operations. But if it's not, then and you have some functions so you can calculate these matrix vector operations, then that's another. Yeah. So we are hoping to expand into those things because if we don't, Newton's method or second-order methods is not going to be like something you can do with Optim if your problem is large. All right. So I will just end by saying that I'm very grateful for Kortner and NRECEP because they do a lot of work on especially the line search algorithms. But if you have any interest in some of this, we're always looking for more contributors because as you can hear, there's a lot of improvements to be made. We're not that far along yet, but I do think that it's very nice to have a good alternative for optimization, unconstrained and constrained in Julia because you can use all these nice forward diff packages and weird inputs just by using multiple dispatch to correctly handle all the addition and whatever. Yeah, so hopefully next year I will have another presentation with constrained optimization in Optim and handling sparse big problems in Optim and stuff like that. I think it's very likely that it will be there for next JuliaCon. So stay tuned. Yeah, so we still have some time. So if you want to look at if you want to try out Optim, I will be here and you can ask questions. If you want to do the exercises, you can do that, or you can just work on some other problem, or just take a cup of coffee or whatever you want to do. But thank you for listening anyway.